Good morning. A very warm welcome to Newnham College on this cold and wintry day for the second full day of our programme celebrating Cecilia Payne-Gaposchkin and astronomy at Newnham and Cambridge in general. We were kicked off wonderfully last night at the Institute of Astronomy. I'm very grateful to the Institute of Astronomy and Sarah Carthew and my development team here for organising this wonderful weekend and for such an amazing array of speakers that we've got coming up for you for the rest of the day. And it seems extremely fitting that today's events kick off with Professor Hiranya Peiris, who holds the Professorship of Astronomy 1909, I like the way it says 1909 after it, at Cambridge, the first woman to do so in the 115-year history of this prestigious chair. Her research covers a wide range of disciplines within astrophysics and cosmology, including the study of the cosmic microwave background, galaxy evolution, and stellar dynamics, as well as leading interdisciplinary collaborations at the interface of cosmology with particle physics and condensed matter physics. I'm not an academic, let alone a scientist, but it is my perception that a lot of the most interesting work is at the boundaries of what perhaps more amateur of us might think of as separate, discrete subjects. So it doesn't surprise me at all to find that there's so much interdisciplinary. I think one of the websites said, to put it more simply, if there is such a thing as simple when we're talking about the beginning of life, she delves into cosmic mysteries at the edge of our understanding, reaching back to the very first moments of the universe after the Big Bang. So hold on to your seats. I'm delighted that she's going to talk to us this morning about decoding the cosmos. Hiranya.
Thank you very much. Good morning, and thanks for giving up your Saturday to come and listen to me talk about the cosmos. But I will actually start in the past and with Cecilia Payne-Gaposchkin, who 100 years ago worked out what is the sun made of. And this is a remarkable discovery because the sun is not made of the same composition of matter as the earth is. And at that time, this really discombobulated the great and the good in science because they just could not perceive that the universe might not be like the earth. Okay, so the sun is mostly made of hydrogen and helium, and hydrogen and helium was made in the Big Bang. So in my view, she made the first step towards understanding what the universe is made of. And that is the journey that we continue today in cosmology. And as a cosmologist, I'm very privileged to spend my time thinking about what is the universe made of, how did it begin, what is going to do in the future, and so on. And what makes that possible is a very simple fact, which is that light has a speed limit. So light has a speed limit, which means that when you look out into the distant universe, that's a form of time travel. Even the light from the nearest stars take years to reach us, so we see those stars as they were in the past. And you can repeat this exercise looking further and further back into the distant universe, and you start to see what it looked like in the past, and you can rewind time almost all the way back to the beginning. And if you go back nearly 14 billion years, you see the cosmic microwave background. And this is the cosmic microwave background, or an artist's imagination of it. And so this is the earliest light we can see in the universe, and it comes from a time when the universe first became transparent to light. And this is about 380,000 years already after the Big Bang, but the universe is about 14 billion years old, so this is a baby picture of the universe. And about a decade ago, some of us worked on a project where a satellite was launched by ESA. It was called Planck, and it made a full sky map of the cosmic microwave background. So what you're seeing here is a sort of elliptical projection of this map, and you can see little mottles of light here, which tracks what is the difference from the average temperature of the sky. Okay, so when you see hot patches and cold patches, these are differences between the mean temperature of the universe at the level of 1 part in 100,000. So very, very tiny, tiny fluctuations. And back then, the universe was mostly hydrogen and helium, a tiny little bit of lithium, really nothing else. Um, so by looking at this map at a time when the universe was very, very simple compared to what it is now, we worked out what the universe is made of. And just like Cecilia's work back in the day, when she discovered something very confounding, that the composition of the sun was different from that of the earth, we now have another confounding mystery. So all of the matter that is around us or in the sun or anything that we have ever tested in the laboratory is about 5% of the composition of the universe. And the rest is dark matter, so matter which attracts with gravity, or dark energy, which is some kind of repulsive gravity that we cannot actually explain right now. It's just a name that we give to some substance that's making the expansion of the universe accelerate with time. So this is like here be dragons territory, okay? I'm not going to touch on that in this talk, but just keep remembering that this is easily the biggest mystery in physics. But I will talk about dark matter. So dark matter outweighs ordinary matter by a factor of 5 to 1. And that is a substance that we think we might be able to investigate both in the sky, looking up at the sky, and also in the laboratory. And I'm going to touch on both of those topics today. So the starting point for my talk is that a study of ancient light has revealed a simple but mysterious universe. And in this journey that I'm going to take you through, we keep building on the shoulders of giants. So we started with Cecilia, and I'm going to highlight another trailblazing woman astronomer that enabled my field, and that's Henrietta Swan Leavitt. And you probably heard about Hubble, if you know anything about cosmology. So Hubble, again about 100 years ago, discovered that there were other galaxies. And the method that he used to do that was the so-called Cepheid period luminosity relation, which was discovered by Henrietta Swan Leavitt in 1912. And I'm not going to explain the physics of that to you, but it is a method for measuring distances to objects. It's still one of the most accurate methods we have available to measure distances to objects, and it will come up later in my talk because that is still one of the outstanding, really challenging problems in my field, how to work out how far away things are. Okay, but this is the beginning of essentially cosmology. We discovered that rather than being static and unchanging, like everybody had imagined before that, including Einstein, the universe was changing with time. It was expanding. And this started the field of observational cosmology. So we have now for some decades been mapping the universe in starlight. So galaxies are mostly made of stars. Stars are like our sun. And so we see light from the sun. We have evolved to do that because the sun emits in optical light. So that means that you can map the universe in the optical wavelengths. By optical, I mean the sort of light we can see. And then we can make maps of galaxies, tracing out the structures in the universe. So what you're seeing here, it might look like an animation. It's not. It is part of the Sloan Digital Sky Survey. And each of the galaxies that you see here is an actual object in the sky. And it has been arranged into this visualization. And if you look at this, I just could stare at this forever. It's like a swarm of fireflies, right? Clustering together. They're not randomly distributed in the universe. they cluster. And in fact, they're arranged in this kind of pattern that is tracing out the so-called cosmic web. And what you can't see in this image is that there's an underlying scaffolding to the universe. And that scaffolding is made up mostly of dark matter. And there are big filaments and clusters of dark matter, and the galaxies trace them. And we have a lot of evidence for that. But we still don't know what is this dark matter. And to work that out, we are currently bringing together big tech, big data, and big algorithms. And I'm going to actually take you through each one of these technological marvels and the data it's going to bring us, and how we're going to put that all together to be able to actually unravel the mystery of dark matter. So big tech. We are very, very privileged as astronomers right now to have many new eyes on the sky. And I've highlighted a few of these projects over here. This is the dark energy spectroscopic instrument. I'm not going to talk about it much in this talk, but it's so cool that I will tell you a little bit about it. Imagine 5,000 robots on a single telescope. Each robot is staring through a fiber at a galaxy and taking what's called a spectrum, which I'll come to at the later stages of my talk. And so imagine these robots by themselves every night when it's clear. You know, some are taking data on galaxies, some are moving into position, some are preparing to go to the next set of galaxies. It's really super cool. And it is a technological marvel. This is a satellite mission that was launched by ESA. This is a mission that from high plateaus in the Atacama Desert is actually going back to measuring that very earliest light that we can see in the universe. And this is the project that I'm most excited about and the one I work on, the Vera C. Rubin Observatory, which is going to start its program of observations later this year. Here is a picture of the Vera C. Rubin Observatory. It is situated also on a high desert plateau in Chile. And you can see the facility here. It is an enormous facility. And you can actually see that the dome is open and there's the telescope in there. And this is an image that was taken when the dome was open, essentially to receive the first light. This observatory is the first major observatory that is named after a woman. It's about time, right? Okay, so this is the third trailblazing woman astronomer that I'm going to present. It's Vera Rubin, who has been a personal inspiration to me since I was an undergraduate. And she was a pioneer of making observations on galactic rotation curves that really solidified the evidence that there is dark matter and it outweighs normal matter by large factors. And hopefully, throughout this talk, it's coming across that the thing that drives scientists like her and like us today is the thrill of discovery. And she said, don't shoot for the stars. We already know what's there. Shoot for the spaces in between, and that's where you're going to find new things. And the observatory that's named after her is going to do that. It's going to open up vast discovery space where we observe the sky in a different way than what we did before. And when you do that, you find new things. So I was very lucky to actually visit the Rubin Observatory as it was being built. So this is in December 2023. It took some doing to actually get permission to go there. And you can see that I look very excited. I'd been, by that point, working on that project for 10 years. And it was when, you know, the engineering drawings that you look at all those years, and you see it there, and it's enormous, and it comes to life. So here is the camera that is being installed on the telescope. So that was in March 25, earlier this year. This is the largest digital camera ever built. And it's like the size of a truck, as you can see. And it observes the sky in very, very big images. 45 times the size of the full moon on the sky is a single image, 3.5 gigapixels. Okay, so, this is like, okay, an image taken from this camera, you need 400 Ultra HD TVs to display one image. It has so much detail. And it's very strange because, usually you like to show lovely images from a camera when you're actually presenting in an outreach talk. I actually can't do that. There isn't enough resolution on this screen or even my computer screen to see that level of detail. And the image is so large, it'll break my presentation software if I tried to show that to you. Okay, so you can see that the camera is actually being installed in here. And then in April, we had the NSST camera see its first photon. You can see from the faces of these people, the thrill of discovery. They're seeing these images for the first time. And, many of these people have been working on this project for far longer than me. It's basically been going for quite a long time. Actually, there is a Cambridge connection, which is not often appreciated. Roderick Willstrop at the Institute of Astronomy in the 1980s actually proposed the type of mirror design that is now used in Rubin Observatory. And at the time, the UK did not actually follow his plans, but the US did. This is a common pattern in astronomy. We come up with the ideas and they implement them. And so in the year 2000, the US decided to build this 8-meter version of Willstrop's design. And I'm going to show you a tiny, tiny, tiny part of a Rubin image, because as I said, I cannot actually display the full thing. And you can see here, this is a bunch of galaxies in the outskirts of the so-called Virgo cluster. And there's so much detail in this image. And this is a very small part of a huge image that is like 45 times the size of the full moon on the sky. And here is a previous image from our deepest currently available data in this same part of the sky. And hopefully, the lighting in here is possibly not great, but hopefully you can see the detail that is revealed by this amazing facility. So that's the big tech. What it's going to do is to produce big, big data. Okay, so what Rubin is going to do is it's going to do this legacy survey of space and time, LSST. It's going to image the entire southern sky roughly every 3 days and do that for 10 whole years. So what happens when you string images together? You get a movie. We are going to make a movie of the universe, and this will allow us to delve into the depths of space to study dark matter and dark energy. It'll make this movie of the universe. We will also make a map of the Milky Way and enable very intricate studies of dark matter within galaxies. And we will also make an inventory of the solar system. And one of the missions of Rubin Observatory is to actually tag all of the near-Earth asteroids that are going to potentially hit the Earth in the future. So it has scientific missions ranging from our own solar system to the study of the whole universe. And that's about 500 petabytes of processed data by the end of the survey. And it's going to come at us at 20 terabytes a night. There'll be 10 million alerts a night saying that something interesting is changing on the sky. And we'll have to work out how to follow up those triggers and work out what are the new discoveries we can make. So this is not my field, but it is so cool. I have to show it to you. Okay. When they took the first light images in order to make a big press release, they found, just in 10 hours of observations, 2,000 new asteroids that were previously unknown. And here is a video showing that. So this is using this new observing capability of wide, deep, and fast at the same time. And so those asteroids, it was just pointing in some direction. And this is the Earth. The asteroid belt is around us. And it's a slice through that. So some are close, some are far. When I saw this, I had this unexpected emotional reaction to it, because you see you think about the universe as a static, unchanging thing. You can't help doing that as humans, but it's literally like alive. So I thought that was amazing. Okay, so let's go back to the dark matter. So, I showed you a lot of big tech, but I want to show you also some old tech. This is a demonstration, pretty old school, which was made by Malcolm Longair at the Cavendish Laboratory. And he uses this demonstration to actually show students something called gravitational lensing. And this is one of the methods that we will learn about dark matter with. And what you see here is a lens, but it is not a normal lens. It is a lens that is shaped like the potential of a big galaxy cluster. Okay, so dark matter creates a gravitational potential. And here is one, it's a lens that is built, shaped like that. So then he puts something in the background like galaxies, and then you can take the lens across this image and observe an effect which is analogous to Einstein's theory of the gravitational bending of light. And that is how we can learn about dark matter. So I will play this video, and hopefully you can get the point much more visually than me just going on about it with words. So here the lens is lensing a grid in the background. And you can see that if you stare down the barrel of this lens, there's a lot of bending of light. In the outskirts, not so much, right? But there is still an effect there. So this is, again, imagine this is a galaxy cluster. And in the background, you can see that there's a lot of distortion due to the gravitational bending of light. So hopefully you got some inkling of how that works. So by observing this foreground, the lensing effect, you can work out how much matter there is in the foreground. And we don't have these lenses yet from Rubin Observatory because that hasn't started yet. But this is an image taken by the James Webb Space Telescope. And you can see here a gravitational lens, which is a big cluster of galaxies. You can see an effect which is very similar to this lens demonstration that I just showed you. And so there's a lot of matter here. And by looking at all of these distortions of images of background galaxies, you can actually work out how much matter there is in the foreground, which you can't see, but you can work out how much there is. And we can use strong lenses like this, or you can also use weak lensing, which is what happens to galaxies in the field, very far away from these big concentrations of matter. And this weak lensing actually makes the shapes of galaxies distort by about 1% on average and displaces them. That's a tiny effect, but we are at the level with our technology and our algorithms that we can actually even use that effect to measure maps of dark matter as a function of time. So I said that measuring distances in the universe is still a very hard problem in my field. So Henrietta Swan-Leavitt's method of using the Cepheid period luminosity relation was one of the most accurate probes we still have today, but it requires you to observe variable stars, and you can't use that method except in the very local universe. So if you want to make maps of dark matter in the distant universe, you have to use other methods. And this also links to Cecilia Payne-Gaposchkin's methods for actually working out the composition of the sun. So I want to spend a little bit of time telling you about science and how it works today. I hope that's okay. There's some cool stuff later to take that bitter medicine, go down. Okay, so hopefully you've seen rainbows. I mean, it's raining all the time now, so hopefully you see them. This is an image I took in Iceland a few years ago, and you can see a beautiful rainbow. So what is a rainbow? So you have sunlight, and there's droplets of water in the atmosphere, and they act like little prisms, and they break apart the light. And that we call a spectrum. So here's a spectrum of the sun. So you can see here wavelength of light and the intensity as a function of wavelength. And you can see that basically the sun has a very smooth spectrum. Okay. So using spectra of the sun is how Cecilia worked out its composition. And so this is very, very much at the heart of astrophysics and how we work out many of our observational results. So you can see the spectrum of the sun here. We have, incandescent light bulbs in this room. This is what happens if I were to give you all a diffraction filter and asked you to hold it to your eye. You would see the light of the light bulbs spread apart like this. So there's just an image of that. And the spectrum of a light bulb looks like this. Okay, so you can see it's quite different from that of the sun, right? And this is what you would see if you looked at a hydrogen lamp. And hopefully you can see that there's basically a few colors, right? There's a purple color, there's a blue color, there's a red color, right? It's not a broad spectrum light. And hopefully, if I asked you to guess what its spectrum would look like, I'm not going to ask you, don't worry. This is what you would see. So this is the spectrum of a hydrogen lamp. And as you can see, it's got 3 colors, right? These are the so-called Balmer lines of the hydrogen atom. These are hydrogen atom lines in emission. What Cecilia used was similar lines in absorption in the solar spectrum to work out that it was mostly made of hydrogen and helium. But these lines actually are what we are going to use in order to work out how far away things are. And why is that? It is an effect called redshift, okay? So when you look at galaxies far away, you see their light shifted to the red. Their light is literally stretched out by the expansion of the universe. And we can, in the laboratory here on Earth, measure the positions of these lines as a function of the wavelength. And this is determined by quantum mechanics. It's a fundamental property of this type of atom. And then when you observe a distant galaxy, you see the lines shifted redwards to longer wavelengths. And when you look at even more distant galaxies, they're shifted even more to the red. And very distant galaxies have them shifted extremely to the left, okay? So by measuring the positions of known lines, you can work out how far away things are. So it turns out that this is an extremely good method for working out how to get distances to distant galaxies. However, even though we have big tech, we still do not have the big tech to be able to take these spectra for billions of galaxies. So the Rubin Observatory that I introduced to you does not take spectra. It takes pictures in 6 colors. So 6 colors that average over these wavelengths. So from those 6 colors, we have to back out the information that tells us where these lines are. Okay, so it's a really, really hard data analysis problem. And that is going to get me to the big algorithms. So some of us realized a few years ago that to decode the cosmos from surveys like Rubin Observatory, where you don't have the spectrum, but you have colors, a number of colors, we need to understand the colors of galaxies in the universe extremely well. And the methods that we are using to do that rely very heavily on modern AI algorithms. And I'm not going to tell you the technicalities of this, but I will try to give you a hint of how we use these algorithms in order to try to understand the distribution of galaxy colors in the universe. So imagine that galaxy colors are actually governed by a large number of properties. I can't visualize n-dimensional spaces, but I'm just going to project it down to 2 dimensions so you can actually get the conceptual point. So imagine that there is a distribution in the universe of galaxy properties. It's not everywhere in this space, it's on some manifold, right? And we want to build a model of that. And here's, let's say, is our starting guess. It's a terrible starting guess, right? It will not come up with the actual colors of galaxies in the universe. So basically, these galaxy properties determine their colors. And we want to work out what is this underlying truth in the universe that produces the galaxy properties, sorry, the galaxy colors that you see in the universe. And what we use here is an approach called forward modeling, which heavily leverages something called generative AI. And so first look at this plot. These are noisy colors measured by instruments of real galaxies, right? And they have this funny sort of crescent shape here. This is just for illustration. Usually we have, say, many colors here, and these distributions don't look exactly like this, okay? But I've illustrated here the noisy colors of real galaxies and the bad prediction made by my model, okay? So what I'm going to show is how we actually calibrate this model so that in the end, we reproduce the actual observed colors, okay? So these are noisy colors. Here are not noisy colors, the intrinsic colors that when you add instrumentation noise produces the noisy colors. And here is the mapping from my physics model to the intrinsic colors, okay? So we do the usual machine learning thing of making my forward model here match the noisy colors. And that allows me to calibrate the model that reproduces these observed colors, and that gives me the truth. And we were very pleased to be able to finally achieve this very, very challenging data analysis problem actually a couple of years ago. And so we are very excited about being able to use this on Rubin data. In the final few minutes, I want to turn to how we can get beyond phenomenologically observing and characterizing dark matter to actually discovering what dark matter is made of. And in other words, is it a particle? And if so, which particle is it? It clearly isn't not a particle that we know about. And theorists are extremely clever and very creative, and they have come up with many, many, many particles that dark matter could be. And the mass of the dark matter particle actually varies over enormous orders of magnitude, which is one of the issues. But I do have a favorite dark matter candidate. And one of the reasons that I really find this candidate compelling is because it wasn't invented to be dark matter. It was invented to solve a really fundamental problem in particle physics. I'm not going to actually explain the particle physics to you, but I'll tell you a little bit, give you a hint of why it is a very big problem. There is a very fundamental property of particle physics called the neutron-electron dipole moment. And this could take any value that you could think of. And then particle physicists went and measured it. And it was extremely close to zero. This is something that physicists call an extreme fine tuning. And physicists don't like fine tuning because it means you have to set numbers by hand, really fundamental numbers by hand. And that is never good because it means there's a big hole in your understanding of physics. And the particle that I find very compelling was proposed to solve this problem naturally, to drive this parameter to zero or very close to zero naturally. And it's called the axion. It's actually named after a detergent because it was supposed to wash away the, the problems of the standard model. Okay, so finding the axion is not the sort of thing that one does at CERN, for example. It is actually very different, and the methods that we actually use to find the axion does not require an enormous facility to be built and for thousands of people to work on it. It can be done in a university laboratory by a small team of people. That is another reason I find this very attractive. And finding the axion is a bit like tuning a radio. We don't know what is the mass of the axion, so we have to sort of tune to a frequency that corresponds to its mass. And this idea is called Sicky's haloscope. And what you do here is that you build a cavity, and within that cavity, if the axion is the real dark matter particle, there will be very large numbers of axions within that cavity, just like there are many dark matter particles, presumably in this room. Okay? So the axion has a very low probability of converting to a photon, which is a particle of light. And that conversion produces a very small electric current. Let me tell you how small this is. So, how many of you have heard of the Voyager spacecraft? Right. So the Voyager spacecraft has a radio transmission capability, and it's currently beyond the edge of the solar system. Right. It's way out there in space, and from the transmitter on the Voyager spacecraft, we can get a radio signal. It's very faint, and we have to listen for it extremely diligently with the Deep Space Network to catch that. And we know what is the frequency, okay? The signal that will be generated by this axion to photon conversion is much smaller than that. So it's a really hard problem. And so you have to build something called a resonator, right? And I also just said that, in the case of Voyager, we knew the frequency to listen to. We know where the station is. We can tune to it. Here, we don't know what is the frequency. So this thing better be allowing you to scan across frequencies, just like a radio. So we are actually building a device like this. And I got involved in this project a few years ago. And you can see that basically, this is a resonator that allows you to listen into that frequency. And this is actually quite a large one. And you can see the scale of it relative to a human. Here is another prototype for a resonator. And here are some of my colleagues testing the natural frequencies of these resonators, so we are not actually fooled by effects in the room, and we can actually work out what are the real axion effects and what are not. And finally, this is the latest prototype that we are working with. We're testing components of this prototype here in Cambridge. And I like this one because, it actually reminds me of the spiral arms of a galaxy. And this one has the capability of tuning, because what it does is it actually, these rods, the separation between these rods is the natural frequency of the system. So if you change that separation, you actually change the sensitivity to different masses. So you can then tune and you can scan. And it is a very elegant design because there's only one central rod. So the mechanical motion is only coming from there. So it's actually, in terms of an experimental approach, very, very so mechanically stable. And then we're going to put this into a very, very big magnet and cool it down to very low temperatures. And we are going to listen to the universe. I've actually got here a a resonator that is a model of the system you're going to put in. It's going to be even smaller than this. Hopefully you can see that it's got the spiral pattern. And I can actually sound this with my hand so that you can hear the natural frequency. Can you hear that? So we are able to, with devices like this, listen to the universe and try to decipher what it is telling us about dark matter. And on this voyage of discovery, I hope there are young people in this room. I hope some of you can join us in the future. And with that, I'll end my talk. Thank you very much.
So you started with that wonderful quote, the reward of the young scientist is the emotional thrill of being the first person in the history of the world to see something or understand something. And you've captured that ongoing excitement and your excitement about the Reuben Observatory. So thank you so much. We've got time, I think, for a couple of questions. So if someone could bring me the microphone.
Thank you for a fascinating talk. This is probably a very naive question, but I have always understood the phrase of the universe to be everything that exists in the physical world. So if it's expanding, what's it expanding into?
Classic question. When astronomers talk about the universe, they talk about the observable universe. So that is the part of the universe which light has reached us from since the beginning of time. So that boundary used to get larger and larger. Now it's contracting because the acceleration of the universe is lowering the size of that horizon. So this is a question that is challenging to answer because it involves concepts from general relativity that are really, really hard to explain in words. But there is stuff outside our observable horizon, and that is still the universe. And there are theories of physics of quantum gravity that tell you that our universe is embedded in a matrix, and there are other universes as well. So if you think about this as what exists, since the beginning of human history, we have found that our conception of what is the universe gets bigger and bigger. We started on the Earth, we went to the solar system, we went to galaxies, now we're measuring billions of galaxies. to me, it's not at all implausible that there are other universes. And that is another part of my research, but it's a different talk.
Yes, fantastic talk. Thank you. I was just wondering if there's any, apart from the fact it's fascinating, is there any practical application, or would there be, from finding out what dark matter actually is?
There probably is. That is not why we do it. We do it for the fascination. But presumably, if we discover new particles, we are going to be able to do stuff with them. So I can't answer your question because I don't work on applications necessarily, but take the theory of general relativity, which underpins our study of the universe. The applications of that theory, which came across to the people at the time it was being proposed as completely esoteric, are so diverse. For example, your phone wouldn't work without general relativity because GPS would not actually work. So from those perspectives, I can't tell you what is the application of dark matter, but there will be one. The technologies that we are building to actually measure the sky and do those kinds of experiments, they push the envelope of what's available. That's the largest digital camera ever built. These robotic systems that measure the sky and the dark matter resonators that we're building, these technologies already have applications beyond the field in which we're actually developing them. So, yeah.
Time for one or two more questions. It's got one here.
Thank you very much. Has a dark matter particle been seen?
No, that is a thrill of discovery. We are looking for it very hard.
I thought I'd seen something recently that somebody thought they might have found one, but that's not the case? So.
Okay, so there was a press release, which I have seen, by a gentleman in Japan, where it was claimed that they have identified a indirect signature of dark matter. We find indirect signatures of dark matter all the time, right? When we make maps of the dark matter in the galaxy from gravitational lensing, we are seeing dark matter in some sense. This was a particle physics signature that this guy claimed to have found. That does not give you a dark matter particle per se. It allows you to narrow down which types of particles might give that signature. I actually think that even that particular signature requires verification. So I think it's a bit premature, that press release. Yeah.
And then I think we've got time for one final question. Anybody towards the back? No, we'll get somebody here.
If I remember correctly, going right back to the beginning,
Yes.
You mentioned dark energy, but you weren't going to cover it.
Okay, yes.
And it said, I think, known since 1974, was it? But what does known mean in that context?
Oh, I see. It was 1980s that I've said known. So let me actually see what I said. Okay, in 1998, there was definitive evidence of the accelerated expansion of the universe. Okay, so suspected since 1980s. That was again an indirect, inference based on the fact that if you looked at the age of the universe using different probes, the numbers did not add up. And that allowed astronomers to infer that there must be a missing ingredient in our understanding of the expansion of the universe. One of those astronomers is here in Cambridge. He was the previous holder of my chair, and the observations for that inference were also done here in Cambridge. So they suspected that there was this missing piece. However, in 1998, that is when astronomers made precise enough observations of the expansion of the universe to work out that it's accelerating definitively. So that 1998 result required observations of supernovae, which are exploding stars, and that led to the Nobel Prize. And similarly, in the case of dark matter, it was suspected since the 30s because essentially, again, the numbers didn't add up. But it was actually Vera Rubin's work in the 70s that made those observations so precise that there were no holes left and people became convinced that there is dark matter. So there is a story to all of these discoveries, and it builds on people's intuition and then finally gets confirmed by data.
I feel one of the privileges of being at Cambridge is the chance to sit at the feet of people who not only understand these amazing things, but because of their teaching responsibilities, are passionate about communicating them. And I think we can all agree we've been taken on a wonderful journey of exploration. It may have tested some of us, but you've kept us with. If you if you kept me with you, you kept most people with you. So it's really wonderful to have our horizons stretched in this way. So I just want to please join me in giving another round of applause.